Okay, so just to recap what I was saying, if anyone had joined later. So we talked about the data path so far in the previous class, different elements of the data path like the register file, ALU, memories, instruction memory, data memory, adders for the instruction fetch mechanism, and multiplexers to control different inputs, and things like sign extending and shifting that needs to be done for immediate operands. So today we are going to talk about the control unit. First, we are going to talk about the control signals that are needed by the ALU to decide what operation should be done for a given instruction. After that, we will have a look at the other control signals generated by the control unit. So when doing this, we are going to stick to a subset of instructions: load word, store word, branch equal, and R-type instructions, which are arithmetic, logic, and shift operations. So this subset of instructions cover almost all the hardware in the data path and the control unit, except for a few signals which are used by jump and I-type arithmetic logic instructions, which we can have a look at later. So for now, we'll be focusing on these subset of instructions. Right. So the ALU is used to perform different operations for this selected set of instructions. So if you take the load word and store word instructions, they are immediate type. If you remember, there's an immediate operand, and offset of the memory address is given as an immediate operand. So in load word and store word instructions, the function performed by the ALU is addition, basically adding the offset given in the instruction to the base register to generate the memory address to be accessed. So the ALU will be performing addition operation. Then for branch if equal type instructions, branch if equal, and very similar to other branch instructions as well, but branch if equal instruction, the function performed by the ALU is subtract. Branch if equal instruction will give you two register operands, register numbers. So the instruction, what it needs to do is subtract one from the other, check the result. If they are equal, the result should be 0. So in that case, that 0 signal or output coming from the ALU can be used to make the program counter change to the correct target instruction to make the jump happen, make the branch happen. So the function of the ALU for that is subtracting the two register operands given by the instruction. So that is for branch if equal. And all R-type instructions, the function depends on the funct field at the end of the instruction encoding. If you remember, last 6 bits, if I am correct, yes, last 6 bits of the, or least significant 6 bits rather, of the R-type instruction defines a function, whether it's addition, subtraction, logic, and logic, or whatever the operation is defined by that last 6 bits. So in that case, the function of the ALU depends on that funct field coming from the instruction itself. Now, these are the ALU, these are actually some of the ALU control signals, bit patterns to get the different functionalities. So for example, if you want the ALU to perform the AND operation on the two input operands, the control signal should read 0000. If you provide 0001 as the ALU control input, then the ALU will provide the O operation. If you provide 0010 as the ALU control signal, it will provide ADD. So the logic circuitry inside the ALU should be designed to get this effect. So with 4 bits in the ALU control signals, if you go back to the previous slide, you can see the ALU control signal here ALU operation is decided by the ALU control signal. It is a 4-bit signal. So with 4 bits, you can have 2 to the power 4, that is 16 different operations. But you might not have all those functional units inside the ALU. Here only we are considering a very small subset of the operations. So not all bits are properly maximally utilized in this case. So you might be able to implement this with even 3 bits if you want. But this is a generic implementation. With these particular ALU control signals, you get that function. So that is how you should implement if you were to implement the MIPS CPU. Right. So, okay. So how to get these ALU control signal, how to generate these control signals as we need here is what we are going to look at. So, right. First of all, we are going to do this in 2 stages. Okay. So in the first stage, what the control unit will do is generate a 2-bit signal called ALU op to decide what categories of function the ALU instructions the ALU will be handling. Then that ALU op signal along with the function code from R-type instructions can be used to generate the actual ALU control signal that we saw before. So let's have a look at the different types of instruction that we are currently looking at. We are looking at load word, store word, branch if equal, and R-type instructions. So if you go and try to find out the opcodes from the instruction encoding, these are what you will find. Load word, the opcode is 35. So 32 plus 3, 35. So that is the bit pattern for the opcode for load word instruction. And store word instruction, the bit pattern is this, it's 43. And branch if equal instruction, the opcode bit pattern is number 4. And R-type instructions, if you remember, for all R-type instructions, the bit pattern for code is 0. The functionality of the ALU for R-type instructions are designated by the funct field, function field at the least significant 6 bits of the instructions encode. Okay, so right. For load word instruction, we should perform, the ALU should perform addition of the immediate operand to the base register value, and therefore the ALU control signal should be this 0010 for addition. And store word instruction also should perform addition. Again, it's a memory access, addition of the immediate offset to the base address value. And again, the ALU control value is the same because it's the same operation, addition. And if you take the branch if equal instruction, the ALU function should be subtracting one operand from the other to check the condition. If they're equal, get the 0 result. So for that, you need to perform subtract operation, and the ALU control signal for that is 0110. So we are just listing different control signals for different opcodes here. Right, and if you take R-type instructions, the opcode is 0, and the ALU function is decided by the funct field. So funct field, we don't really care about the funct field in these load word, store word, branch if equal instructions because they don't have a funct field. Now, in R-type instructions, the funct field will define the ALU function. If the funct field is 100000, you're talking about add instruction, adding the 2 operands. If the funct field is this, subtract instruction. So for different operations of the ALU, the funct field have different function codes. And the ALU control signal should be decided accordingly. So here, the funct field 100000 or number 32 means add operation for an R-type instruction. And the ALU control signal for add operation we already know is 0010. So the ALU control signal generated by the control unit should be that. Right, and for subtract we already know the ALU control signal 0110. So that should be the same for R type instructions which uses subtract operation. So likewise you can understand the rest of the table here. So any questions you have, any questions you're having so far, you can ask. So the control unit's purpose is to, at this stage, to control the ALU, is to generate this ALU control signal, a 4-bit signal based on the incoming instructions opcode and the funct field if appropriate. So the control unit should have some sort of a combinational logic function or a set of combination logic functions to derive these separate bits of the ALU control signal. Like I said, we begin with, at the first step, we will use this, we will derive an ALU op signal, a 2-bit signal, purely based on the opcode. So since load word and store word use the same ALU functionality, can use the same opcode for that. And branch if equal uses a different ALU function, different ALU op signal for that. And all R type instructions, you should consider the funct field as well. So for that, we generate an ALU op signal 10, or rather 1, and don't care. The second bit, the least significant bit is don't care, but it's better to have it as 0. So the control unit will first derive, based on the opcode, it will first derive the 2-bit ALU op signal. And then in a second stage, it will derive the ALU control signal based on the ALU op here, which was first generated, and the funct field if appropriate. So I hope you can now imagine how these can be generated with ALU with combinational logic. So I would recommend you to, after the lecture, try to come up with logic functions, combination logic functions to generate these signals. For example, ALU op signal, you have 2 bits. So these 2 bits are the outputs. Inputs to your logic function are these 6 bits of the opcode. Now, keep in mind, we are only talking about a subset of instructions, right? So you can only use these particular opcodes. But if you're talking about all other different, all the possible instructions, you have to consider all possible opcodes available in the ISA. But in this example, we only consider these 4 types of opcodes for ease of understanding. So what you can do after the class is maybe you know the methods from digital design. You can start with a characteristic table. These are the inputs, right? 6 different inputs, 6 input bits. Opcode 0, opcode 1, opcode 2, opcode 3, 4, and 5. Right, 6 different inputs and 2 different outputs generate the ALU op. So you can use the standard methods. You can use Kano maps or whatever to derive the combinational logic function and simplify it to generate these 2 ALU op signals from the opcode input. Then you can have another separate combinational set of combination logic functions to generate the 4 bits of the ALU control with ALU op and funct fields as input. So in the second combinational set of some combinational functions, this ALU controls 4 bits are the outputs, and inputs are ALU op 2 bits and funct field from the instruction 6 bits. So based on these 8 bits of input, generate the second ALU control signal, which is actually sent to the ALU. Is that clear? Do you guys understand how this is to be done? Is that clear? Any issues? Okay, I take it there are no issues. So after the lecture, you can go and try to derive the logic functions for ALU op signal and then using that ALU control signal. And that is actually how this is in reality implemented if you were to implement the microarchitecture. So that exercise, if you go and try to do that, will give you a lot of understanding, better understanding of how this happens. Right, so that is controlling the ALU. The control unit should generate this control circuitry to generate this signal. Now, can someone tell me why do we do this generation of the ALU control signal in 2 steps? Can someone make a guess why this is done so?
Because there are some controllers, same control in the ALU for different opcodes.
I'm sorry, I didn't hear that properly. Can you repeat that, please?
In ALU, there can be the same control, ALU control for different opcodes, like the same function in the ALU happens for different opcodes.
Yes.
To generate that.
Yes, so that answer is partly correct. The idea is for, say, half of the available instructions, you don't need the funct field and you only need the ALU op field. So you only need the opcode. Then the ALU op field can be directly translated into ALU control very easily. The only R-type instructions will need the funct field, and that is designed for a specific purpose because you need say that's a design trade-off between having a large number of immediate bits in the instruction to have large immediate values, as well as having a large number of instructions as much as possible. So because of that, the func field is separate for type instructions, and because of that, we are generating the ALU op signal first and then generating the ALU control signal. And also another reason is the control signal for the ALU, the actual control signal, it's okay to be slightly delayed compared to the other control signals that are generated by the control unit, which we are not looking at the moment. We will have a look at them next. So some control signals should be generated quicker than the ALU control signal, such as what to do with the immediate operand, what to do with an immediate operand, whether you need to shift it, whether the input to the ALU should come from an ALU, the input to the whether the input to the ALU should come from a register file operand or an immediate operand. So those decisions need to be done fast. So doing the ALU op control in 2 stages makes the design of the control unit efficient. So the signals that are needed to be generated faster are not hindered by other large logic circuitry which actually are needed a little bit later. So again, I recommend you to read a little bit on why this is done in 2 separate steps. Right, okay, so I hope the basic idea of generating the ALU control signal is clear now. Right. With that, we should go and look at the main control unit. What other control signals are to be generated here? Right. So these are the instructions that we are looking at. R type, load word and store word, branch if equal. And the encodings are like that. As you can see here, the opcode is 6 bits for everything. Then the layout of the first two register operands are also very similar. So you can find regularity here. If you remember the design principles from our previous chapters in this course, you can find a few different regular encoding patterns here, right? So if you take the first 6 bits, always the opcode. If you take the next 6 bits, an operand, a register operand, other than jump instructions. So a lot of regular patterns here, which simplifies the control unit's hardware. So based on the opcode, you need to send all these different, you need to interpret these different bits according to the opcode and send them to the correct places. For example, register addresses to register file. And in this, the second half of the instruction, or the least significant half of the instruction, if it's an R-type instruction, these bits are func field. If it's a load word store word instruction, those bits are part of the address offset. So interpreting the rest of the instruction should be done by the handled by the control units. That is called the decoding of the instruction. So based on the instruction, based on the opcode and the other parts of the instruction, you should treat them accordingly. Immediate offsets in the instruction should be signed, extended, and added on top of a base register address. And in R-type instruction, RD is the register to be written to. That is the destination. In load word and store word, RT is the register to be written to. In branch instruction, RT is a reading register. You should read that register. RS is always a read register for all three types of instruction. And RT in R-type instruction is also a read instruction. So you read these two and write to RD. Load word store word, you read RS, which is the base register value, and RT is write for load. If you are loading from the memory, you write to that. Otherwise, this is the data, you are reading this and writing it to the given memory address, computed memory address. So RT is read for store word, write for load word. And in branch if equal, RS and RT both are read. So you need to treat these operands differently based on the opcode. So the control signal should derive the control signals for the multiplexers, sign extension units, and all those things to treat these different parts of the instructions accordingly. Right, so this is an overview diagram of our data path, the data path that we previously had a look at, with the control unit added for our selected signal, selected instructions, load word, store word, branch if equal, and R-type instruction. So you can see the control unit is generating a set of control signals in blue color here to control different parts of the data path. For example, if you take the this ALU op signal, it is a 2-bit signal if you remember correctly. So the control unit generates the 2-bit ALU op signal and it goes to the ALU control signal unit. Here, the second stage of the generation of ALU control signal is happening. So for the second stage, you need the ALU op signal as well as the least significant 6 bits of the instruction assuming that this is an R-type instruction, right? So if it's an R-type instruction, the least significant 6 bits of the instruction will be used by the ALU control, and the ALU op signal generated by the main control will be used by the ALU control to derive the control signal that is going into the ALU. So that is one example of controlling the ALU. And you can see there are a lot of other signals generated by the control unit. For example, this reg DST or register destination, that is generated by the control unit and sent to this multiplexer here. So what is the purpose of doing it? To decide which register you are writing to, decides the address of the write register. It may be bits 11 to 15 of the instruction or 16 to 20 of the instruction. If you go back to the previous slide, you can see for R-type instruction, the destination register to be written into is given in bits 11 to 15, those 5 bits. In the case of a load word instruction, you read from the memory and write the result into RT register, which is given in bits 16 to 20 of the current instructions encoding. So the register to be written to come from 2 different places in the instruction depending on the opcode. So here this control signal will decide whether to take bits 11 to 15 or bits 16 to 20 of the incoming instruction as the writing register to be written into. So that is decided based on the opcode. If it's an R-type instruction, we should take that set of bits as the address of the writing register, ORD. And if it's load word instruction, we should take these bits 16 to 20 of the incoming instruction as the address of the writing register or number of the writing register. Is that clear? Is that clear? Say yes or no. Yeah, okay. Right. So based on the signal that is coming from the control unit here. So if that signal is 0, if the value of this control signal is 0, you are taking this input 0 and providing it as a write address of the register. If the value of this signal is 1, you take the input 1 and provide it as the input to the register file's write register. So now I want you guys to do a little exercise. Take about 5-6 minutes and do a little exercise. Make a list of all these signals here, all the register signals, all the control signals coming out of the control unit, and and write down what exactly they do. For example, what we discussed right now, this reg dest or register destination control signal purpose is to decide what is the register to be written into, and if that signal is 0, you are taking bits 20 to 16, or in other words, these bits yeah, if that signal is 0, bits 16 to 20, yeah, these bits. That is in the case of a load word instruction. And in the case of a store word instruction, in the case of an R-type instruction, we are taking bits 11 to 15. So like that, write a small description of what this is done. You can do it on a piece of paper or on a notepad in your computer, whatever. You don't have to share it with me. Just go through this list and write, and I'll ask in 5 minutes. I'll ask from you to give me the answers. The purpose of each of these control signals. Okay, can someone tell me the second signal that you're seeing here after register destination? Second one is branch. What is the purpose of that? Just in a few words. Can someone tell me?
Branch if equal.
Yes.
Um,
For branch if equal instructions, what does the so yeah that signal applies for branch if equal signal instructions. So what does it do? What is it trying to do?
if the max getting that signal is 0,
Yeah.
then it'll add just 4 and go to the next instruction.
Yes, if you send a 0 from here to that mux, you're only adding 4 to the program counter and just go to the next instruction. Or
If not, it will calculate the, it will convert, it will extend the sign and shift it by 2 and
yes,
add it to get the offset, and it will.
yes, exactly. If not, the branch instruction will take the immediate operand given in the branch instruction, shift that sign extend that to 32 bits and shift it to the left by 2 to convert it into a byte address and add it to PC plus 4 and make the appropriate jump based on that. So yes, thank you. Very good. So can someone tell me about memread? Memread signal? What is the purpose of that? It's very simple actually. What does this signal do? Memread. The control unit is reading the opcode of the instruction and generating that memread signal to be sent to the data memory.
Whether to read data from the given address.
Yes, if you need to read data for a given address. So this signal will be set to high or set to value logic value 1 if your instruction is a load instruction, if you are reading from the data memory, right? That is the idea. If you're reading from the data memory, this signal is set high. Remember the write enable signals used in registers and memory, write enable or read enable signals. So that is one such control signal. And very similar to that, mem to reg signal. Somewhat related to that. So before that, mem write signal. Let's talk about mem write signal before that. That signal will be set high for what instruction?
Whether write to write data to the given address.
Yes. So the signal will be set high when you need to write data to the given address. That is in stored instruction, right? That is the operation of the stored instruction you are writing to the memory. So if your instruction is a stored instruction, which can be decided by looking at the code, this memory write signal will be set high and the memory will do a write operation. So okay, so after that, mem to reg signal, this fourth signal here, mem to reg. it is sent to the multiplexer, which is at the output of the data memory. Control unit looks at the opcode, generates this mem to reg signal, and send it to this mux. What is the purpose of that signal?
If it's 0, it will get the direct result from the ALU to the given register.
Yes, if it's 1.
If not, if it's 1, it will get the data from the data memory to the register.
Right. So if the control signal is 0, you're getting the input from the ALU's output. ALU's result is the input to the multiplexer. If the signal is 1, the input to the multiplexer from the data memory's read port is selected. So the idea here is, if you look at trace this signal, the output of the multiplexer, it is going to the right data port of the register. What data are you writing into the register file? Are you writing into the register file the output of the ALU, or are you taking the output of the data memory and writing it into the register file? So the idea is, if you are dealing with the load word instruction, you should take the data memory's data and write it to the register file. If your instruction is an R-type instruction, then the result of the ALU is your result that should be written into the register file, right? So to do that selection, you do this mem to reg control signal. If mem to reg is 1 or true, then you select the memory's output. Otherwise, you use the ALU's output. Okay, I hope this is clear. Then ALU operation we discussed earlier, mem write we also discussed. Then ALU source, ALU SRC. What is the purpose of that?
Selecting whether the ALU second input is from the register or an immediate operand.
Exactly. So the purpose of ALU SRC or ALU source signal is to decide the second operand or the second source of the ALU. First operand is always coming from the register file. Second operand of the ALU or second source of the ALU might come from the register file or the instruction's immediate value. So selecting between those two is what that ALU source signal is for. If you have a 0 on that signal, you're taking the register file's operand into the ALU second input. If the value is 1, you're taking the immediate operand, sign extended, into the ALU second operand, as the ALU second operand. So I hope now you understand the control logic, the idea behind these various control signals. Now. Then the final one here is register write, and that is very simple. Whether you are going to write to a register in this instruction, write control. So some instructions do not do write. Like if you take a branch instruction, they do not write to the register file. R-type instructions, they do write to the register file. Store word, they don't write. Load word, we do write to the register file. So only for instructions that are writing to the register file, this signal will be set high, and that can be decided by looking at the instructions opcode. I hope this is clear to you. Are there any questions?
So is it necessary to have separate controls for memread and memwrite?
Good question. It appears in this particular case you can only do with one signal, right? If the signal is 0, this. If the signal is not 0, that. Yeah. So it appears like that. But if you let's see if I can bring up the slide. If you remember those control timing diagrams, with write control and read control. right? So I hope you're looking at the slide I'm showing. Um, you can see that the write signal is used to decide when to write into the memory, right? So at that clock edge, if the write signal is set high, you take the data from the D input into the Q state, into the state of the reception circuitry at the memory, right? The latching mechanism. So that is the idea. So if the signal is 0, you don't write. So having those, that is why you have two different signals. So you can do reads and writes at the same time if required. In this particular example, we are not reading and writing at the same time, so it doesn't make a big difference. We might be able to use one signal and have the design of the data memory to support that, but generically you should be able to write and read at the same time. We'll have a look at that a little later when we talk about pipelined systems, pipeline microarchitectures. You will see that you need to write and read at the same time, and in that case, these signals have to be used like that. Any other question? So since it's already 10, I think we'll have to stop. So we'll keep talking about the control unit in the next class. How the different instructions, different types of instructions that we were looking at, load word, store word, R type, and branch, how they go through our data path and control individually, which hardware they are using, which control signals are activated. We'll have another comprehensive look in the next class. So we'll stop now.